Alright, so here's a video on something called Extrema, and this is a large part of calculus. We do all this work to find derivatives, and we work on finding tangent lines, and we got to get into, like, how is the tangent line helpful to us? And we've talked a little bit about how it applies to physics examples, but I also just want to talk about graphing in general. So here's a picture of a function called f of x. I don't know the equation for this function, but I know that the graph looks something like this. Well, there are definitely some key points that we could kind of highlight here. And those key points happen to be kind of what some people call the peaks and the valleys of the graph. So I'm looking at places like this low point right down here, or this high point up here, this low point down here, or this other high point up here. And I could highlight other areas of the graph too, but these four locations have something in common. And the one thing that I'm noticing that they all have in common is that if I said, find the slope of the tangent line at these points, well, what would the slope be? Yeah, it'd all be 0. Every single one of these, if I was to draw a tangent line, would have a totally flat tangent line. And if the tangents are totally flat, then we know at these particular locations, so like right here, we know the derivative is going to be equal to 0. So for instance, if this point that I drew an arrow to, let's say it's at 2 on the graph, then I know f prime of 2, the derivative at 2 must equal 0. It's got to be a fact. It's got to be a flat tangent line. If this point up here, we'll say, is at 3, if that's at 3, I can erase these dotted lines. I don't need to have that there. If that's at 3, then we know the derivative at 3, f prime of 3, is going to equal 0. And so what's unique is the fact that they all have a slope of 0, and at the same time, they're all either a high or a low point on the graph. And so we refer to these often as max and minima points. If it's a high point, like this point up here, we say this is a maximum value on the graph. It's not necessarily always the max of the entire graph, but it's a high point. For instance, this would be a max over here also, right here. So we got two maxes on this graph. One max we'd call kind of like a local max. It's totally flat right here, and it's a little high point. It's not the highest point of the graph. We would say this point up here, right in this location, is the highest point that we can see on this graph. But two different maxes. Minima are going to be these low points. So here is a minimum value down here, and here's another minimum value. So what we've done is we've kind of broken the graph up on these high and low points, realized that anytime there's a min or a max, we have a derivative equal to 0. And so we name these points, and I'm going to show you the names on the next slide here. We either call them a local or an absolute max and min. Some people use the words relative max and min and global max and min. You can use, they're kind of interchangeable. Local and relative mean basically the same thing. And what these are high and low points on the graph. So if I'm talking about a local max or a local min, then it's a high or a low point on the graph. If I'm talking about an absolute or a global max and min, it's also a high or a low point on the graph, but it's the highest and the lowest point. It's usually given to you on an interval. So it'll be something like, find the absolute max on the graph between 2 and 10. And that means between 2 and 10, find the highest point. So it's kind of the absolute max. The words kind of make sense why it's called absolute. So it's the highest, I'm going to underline highest, or lowest point on the graph. So it's not just a little high point, it's the highest point, the highest or the lowest, and it's usually on an interval of the graph. On an interval. I'll just put that in a parenthesis down here, on an interval. And it turns out, whether you want to call it a local or a global, either way, when you go to these points on the graph and you start identifying them, you know the one thing that these two things have in common is that the derivative is equal to 0 at these points. We have flat spots. So I think that's a big thing to kind of note. So no matter what, we know f prime is equal to 0 at these points. So we have one more scenario that kind of comes up once in a while, and it's this scenario. I drew a new graph here. If I started to study this graph, I don't really recognize any min or maximum values, no high or low points, but I still see a spot where the derivative is equal to 0, where f prime is equal to 0. And that one spot is, wherever it's going to be flat. So I'm thinking right around here, right in this location, right? Sorry, I'm trying to highlight it. There. So let's say that's at 3. I would say f prime of 3 looks like it's equal to 0. If I drew a tangent line, I would guess the tangent line looks something like this. So here's a case where we have the derivative equal to 0, but it's not a min and it's not a max. So just because f prime equals 0 does not guarantee a minimum or a maximum value. Here's a flat spot and it's neither. And so we name these flat spots something else. We call them a terrace point. The terrace point. It's a flat spot on the graph, totally flat. The derivative is equal to 0, so a flat point on the graph. The derivative equals 0, alright, f prime is equal to 0 at this point, but it's not a max and not a min. Not a max or a min. So, in this chapter 3 that we're going to be working on in class, we'll be doing a lot of work with functions and just being able to ask certain questions like, can you find all the minimum values on that function? Or can you find the min and the max? Can you find all the terrace points? And one of our strategies, instead of just graphing it and looking visually, is going to be to utilize the derivative to find all the flat spots. And we'll get into that in some more videos.